I'm okay for now. An hour is about.
We actually have an external speaker for this portion, but they canceled the last minute. And so this week, Jordan Docter and Michelle Chun, who are graduate students, respectively in computer science and physics, so true Q-Farm style interdisciplinary collaboration, have stepped in heroically into this void and volunteered to teach us about some important results that they have that really resolve a 20-plus-year-old open problem at the intersection of quantum algorithms, information theory, and complexity.
Thank you, Patrick. Hi, everyone. I'm Michelle, and then I'll start this presentation and hand it off to Jordan as we go along. So before we get started, I just wanted to say that all of this work is, done in collaboration, of course, with Jordan, but also with Anthony Chen, who's a graduate student at Caltech, Brando, who's an advisor, and Adam and Patrick, who are up in the front here. For today's outline, there's a lot of words in our title, but we are essentially just talking about pseudorandomness. So we are going to give background and motivation for pseudorandomness and why it's important and why we care. And then we'll jump into the specific forms of pseudorandomness and our constructions and things like that. So before we can talk about pseudorandomness, we need to just talk about randomness and why randomness is important. Random unitary matrices are, first of all, important resources in quantum information and quantum computation. So some examples are certainly in encryption. Random unitary matrices play a role. It's not so surprising. In full cryptography, randomness is also used as a resource. So here in quantum cryptography, you would also care about and utilize random unitary matrices. Another example is randomized benchmarking, which is certainly it's a much more practical and current application. Randomized benchmarking, as many of you know, is a way to evaluate the error of many setups in quantum computing. And so you apply sequences of random gates and investigate the fidelity of those. So this is currently important in the development of quantum computers. And another application is shadow tomography, which I believe Robert Huang came and gave a talk about last fall, something like that. But that's a process by which you would like to know properties of a quantum state, but you aren't able, you don't want to destroy it, you don't want to measure it directly. So what are things that you can, investigate about it? And so there are also, plenty of other applications that I haven't mentioned here in communication and coding and otherwise. Needless to say, this is a very important object in quantum information. Random unitary matrices are also important on a conceptual level to the modeling of the dynamics of many physical systems. So in general, chaotic systems, you can use random unit to talk about chaos and scrambling and things like this. And also in black holes and quantum gravity, people care about, some people will use use random unitary matrices to model the dynamics of black holes. And also there are questions about complexity that tie in with random unitary matrices and quantum gravity. So, this object is everywhere. But random unitaries also have limitations. So one of these limitations is that they're very expensive is one way to put it. You can say expensive sort of in a conceptual way, or perhaps you want to actually implement them, costly in a truly physical way. But they're essentially exponentially complex to construct. So they require, there's many ways in which this is true. One way in which this is true is that it requires just so many more random bits than you would normally expect. You can already get randomness in a quantum mechanical system just by measuring something, but a random unitary truly has an incredible number of random bits. The other thing is if you want to construct ensembles of random unitaries, the runtime that you would naively, that you would need to run it for is also exponential in a parameter. So this is just generally a very costly object. Essentially, when we're talking about, we're going to be talking about Haar random unitaries, we are thinking about random on an extremely large space. So, uniformly random on an extremely large space. So you end up with something that's just a very difficult object to construct. The other thing that's also worth mentioning is just that random unitaries are probably unphysical. So they're really great for modeling things, and it's possible to have analytic control over these random unitaries, but most systems aren't going to scramble that fast, and you might want more realistic versions of unitaries in order to model your scrambled randomness. So then this leads us to the very natural question, which is, can we spoof quantum randomness? And you can celebrate because yes, you can, and that's the focus on the rest of our presentation. So essentially with pseudorandomness, which is the study of all the ways that we can spoof randomness. Okay, so now we can jump into specifically more particular definitions of pseudorandomness and categories of pseudorandomness. So in general, right now, people study two different kinds of pseudorandomness or approximations to randomness. One of these, so we'll be discussing both today, although we'll change our focus as we go. The first is computational pseudorandomness. This is something that is actually a little bit newer in its study in quantum information right now. But computational pseudorandomness essentially dictates that, so between your two ensembles, one of which is truly random and one of which is whatever you're constructing, there should be no efficient algorithm in which you can distinguish these two ensembles. So this specifically, if you're looking at unitary ensembles, these are what we'll call computational pseudorandom unitaries. This is also a little bit confusing because in the literature, they're also just known as pseudorandom unitary PRUs. And if you see PRUs, they're usually referencing the computational sense of the word. But there's also a sense of pseudorandomness that has existed for and been studied for longer than the current computational forms. This is a statistical notion of pseudorandomness. So by statistical, I mean T moments are matched. And by moments, one way to conceptualize this is essentially correlation functions of approximately T, like T objects are going to, this translates into something about correlation functions. And statistical approximations to randomness are known as T designs in the quantum information community and K designs in the quantum gravity community. But mostly people refer to them as T designs, so we will refer to them as T designs for the rest of the talk. And first, we will be focusing on the statistical notion and outlining a history and where our work and our construction lies within that very long timeline. So let's get into the definition, much more specifically than just matching T moments. So the intuition that you can have here is having thinking about T-wise independent hash functions. But if you want the very concrete definition, let U be a Haar random unitary. So that's the random thing that we want to compare it to. A random unitary V. So V is actually an ensemble of unitaries, but this is the thing that we construct. We call that an epsilon approximate unitary T design if the following mess is true. So there's quite a bit here to dissect. So essentially, first you can just see that this is the difference between two objects. So one of these objects is something that focuses on the ensemble that we are creating, and it is taking an expectation value over the ensemble V that we are creating. And the other object that we are comparing it to is an expectation value over the actual Haar random ensemble. And we're comparing these two objects within some norm. This is the one norm, which is specifically the trace norm. But if you aren't familiar with that, you can also just think of it as some distance measure between these two ensembles. And we want to say that essentially that these two ensembles are very similar, or that the distance between them in this norm is very small. So epsilon is some small parameter. And it is, the epsilon of the epsilon approximate. And so then to break this down a little bit further, what specifically are we comparing within this one norm? Well, we are saying that T applications, so this is the T of the T design, T applications of the ensemble, be it our ensemble that we've constructed or the Haar random unitary ensemble, tensored with, ancilla dimensions, as you may, apply to some state. So this is just some state rho with the correct normalization, and this ancilla space can be of whatever dimension. You want to show that essentially the state that you're putting through a channel that you've crafted with your ensemble or with the Haar unitary ensemble, well, I guess that they're going to be close to each other. So in order to sort of simplify all of that, essentially we want to say that any state that we put through some process of applying our unitary T times is very close to that state being that state undergoing, some T effect with the Haar random unitary. So that's a lot to take in, but that's our formal definition, that in the end, that's what we're, all the proofs want to end up with something like this. If you're familiar with it, another way to say this is that the T-fold unitary channel, which we've defined here, is close in the diamond. I'm not going to go into that as much, but if that means something to you and that helps you, that's, another way to simplify the notation for this definition. Right. So we want to give a timeline of the history. People have been studying T-designs for a while. This is that should be 2002? Okay. That should be 2002. In 2002, this is studied the Clifford group and realized that it's a 2 design. And then in 2015, which is this other paper, people realized that the Clifford group is actually a 3 design. And so this is a simple example of a design. The Clifford group is something that people easily reach for in quantum computation. It applies to a lot of things. It's a group that is, so we have the definition here. One way to define this is, you think about the poly group, and then you think about essentially this definition with relation to the poly group, what normalizes it. Another way to think about it is that the Clifford group is just the group that gets generated by the Hadamard, the S phase gate, and the Xenon gate. So there's a few ways to think about it, but the Clifford group is an easy object to reach for, and it is an exact 3 design. So the epsilon that we had before is not applicable here. It's an exact 3 design that matches those moments up to t equals 3. But people also think about many other constructions of, and have thought about many other constructions of T designs. So one very popular sort of group of constructions to think about is random unitary circuits. There are many people in the room who think about random unitary circuits for a number of applications, but in this specific case, they are also applicable and can be studied as a T design. So in 2012, Fernando and they studied random unitary circuits and showed that essentially the scaling of the gate count scales with t to the 10th. So here it's different than so when I looked at a Clifford group, we know that that's a 3 design, and that's great, but we can't get anything further than that. But there are constructions where, say, you want a higher design. In a random unitary circuit, well, I guess I'll get to the next slide. In a random unitary circuit, which I've sort of illustrated a very small model of here, as you let that circuit evolve more and more, you will get to reach higher moments. So this is a design, but it's different. It's a design that will end up scaling the amount of time that you end up running. It will scale with the number of moments that you end up achieving. And as we have here, and also on the timeline, so originally it was analyzed in 2012, but people have worked on it for a while and improved that analysis through time. And eventually in 2022, it was shown that it was improved to t to the 5th. So that's quite a reduction. There's quite a few papers in between that I've suppressed here, but people have been thinking about this for a while. And okay, so then we get to this year, and a lot has happened this year, and this is what we'll be talking about. So first, in February, there were, one of the papers from our collaboration, as well as the paper from Halu and Tan, they and we established an O tilde of t squared. So our construction is not of random circuits, but theirs is, and I'll be getting, or Jordan might be getting into our construction shortly. But this is an improvement upon the previous scalings, and it's very interesting also because these 2 papers use very different techniques, analyze very different systems, and nevertheless, we come to the same t squared, which is great. And then much more recently, we have further papers. So our group and also a different group have now found linear scaling. So I'm going to get into that. Okay. We found linear scaling, which is considered to be optimal, and I'll get into that in a second. But that's sort of the current progress of where things are in the T design race. Again, these 2 papers are different methodologies. They analyze different constructions. As we sort of have hinted at with the title and with the titles of these papers, we are looking at random sums, and specifically, we developed a lot of novel random matrix theory techniques in order to reach these scalings. But there's also, the Haar paper, like I said, analyzes random unitary circuits, and the Medgar et al. Paper that is looking at something that they call the PFC ensemble. So, lots of different ideas coming together to think about T-designs. I want to talk more about the linear growth. I just want to mention that it's optimal from a counting argument, but also that this sort of has a connection to holography, to ADS-CFT, in the sense that, people are thinking about the linear growth of complexity within black holes, and this is, while not necessarily, how a black hole evolves, this is also that's going to give us that sort of linear growth. So this is has a lot of connections to all sorts of different things. Right. So like I mentioned, we'll be focusing on or at least for most of it, I guess, we'll be focusing on the first paper that developed the T-squared, even though that this isn't the, I guess, state of the art anymore. All of the techniques that we use in our subsequent paper are developed in this paper. So we'll be going through some of that if we have time. You want to take it now? It's it's around 20 minutes, so we can. Okay, I can continue for. Do you want me to continue for a little bit? Okay, so this is our construction. I've just thrown it on here without much current motivation, but we're going to break down the pieces of it, and I'm going to hopefully give you some intuition why something like this would work. So first thing to notice is just that we have a copy of two things. So one of these things is, they're both of a similar form. So we can analyze just one of them. And specifically, the form is that of an exponentiated, here is a sum of Hamiltonians, but essentially a Hamiltonian. So if you think about implementation here, we are really just implementing some Hamiltonian and letting it develop in order to craft this construction. So, and then we're taking two of them. So two of them is actually really important. Somehow one of them doesn't suffice. There's a lot of matrix theory, I guess, behind that points to that. But it is not entirely an intuitive thing. So there we have two of them, but we can point to specifically the sum of Hamiltonians that we are trying to I guess the sum of Hamiltonians that's featured in each of these exponentials is of these objects Hj. So Hj is going to be some matrix that matches Gaussian moments for low moments. So here it's C for some small c. So an example of this can be the polymatrices. The polymatrices match up to, the second moments of Gaussian. Specifically, when we say Gaussian here, we are referring to GUE, if that means anything to you, Gaussian unitary ensemble. But one way to think about it is just we're taking some matrix with Gaussian entries that's also Hermitian. And they match, so Hj is something that matches those moments up to something very small, and then we add a lot of them together. So we add m of them together specifically. And n here scales with t, so t of our original t design. So that's a parameter that we have to choose. And then something to realize here is that, so I said that we are evolving some Hamiltonian, and here I haven't, well, it would be confusing to use t for Hamiltonian evolution, given that we are already using t, but we have a theta here, which is representing sort of, you can think about the amount of time that you're evolving it for, but here theta is something that's very small and constant. And that's part of the reason why we have to use 2. We don't want to evolve for a very long amount of time because that would be costly. So the theorem here that we can state, this is an informal version. If you look in our paper, there's something much longer and scarier. But informally, the object that I've presented to you here is going to be a t-design in t-squared circuit depths. So this is the final construction of our original paper. This is what we also provide an algorithm for implementing this. This is the object. This is the t-design. I'm going to switch off now. Would you like to?
Okay, thanks, Michelle. Does anyone have any questions about this construction?
What C do you need?
So C You can think of C as just a very small constant. We wiggle around some of the parameters in our final definition. I don't want to get into the details. It actually has to be like log n to get our O tilde scaling. But you can think of it as something that's small enough that we can construct these designs, these H's, efficiently with a quantum circuit. So the whole point of this construction is that we've turned this object into something that, like a complex object, into something that we think we can Hamiltonian simulate or construct efficiently. And that stems from these H's, which are match low enough moments that we think we can construct them efficiently. The best is just to think of them as like Pauli matrices, something very simple. Yeah. Okay, so as I just mentioned, one of the key challenges of constructing T designs is to construct an ensemble that's we think we can implement efficiently on a quantum circuit, and also we can analyze and say that it mixes, it looks very random and is close to Haar. And as I just mentioned, the key component of this mess, which is the same as the mess that you saw on the previous slide, is that these H's are simple enough to construct, and we can actually do Hamiltonian evolution of these Hermitian matrices H. And this is done via something called these off-the-shelf quantum algorithms called LCU or QSVT. You don't need to know what they are, but they exist and we use them. Then you might ask, okay, well, it looks pretty random, but why and how can I know that this is actually random? And you might have noticed, and Michelle pointed out, this is the product of two unitaries. And we first show that these two exponentiated sums are actually close to these two exponentiated GUE or Gaussian matrices. You can just think of these matrices G as the matrix analog of like a Gaussian random variable. So they basically have IID Gaussian entries. And this tilde comes from, or the similarity comes from fact, basically a matrix version of the central limit theorem. If you take a bunch of these H's that match the low moments of your Gaussian, it converges to the true Gaussian. And you know that from your probably classical probability class. And we get the same thing for matrices. And we have two over here, so we also have two over here. And at first we were just analyzing one of these objects. It looks pretty random, but it turns out that that's not close to Haar. Keep going backwards. But surprisingly, if we just take two of those and multiply them together, so apply one of these unitaries and then another IID1, already just two gets us something that's very close to Haar. And this somehow comes from the bases of these matrices are mixing just enough to get us close to Haar. And I won't get into the proof techniques, but I wanted to mention that one of the important or key results of this paper was developing a new technique to show the similarity. And we used a polynomial method to get corrections or to get the finite n corrections, where this n is our dimension size. I don't know, people in high energy might be familiar with that.
It's the reason that you need two of them, because you don't want energy conservation.
What do you mean by energy conservation?
Like if you only had a single one, we would have energy conservation because it's like Hamiltonian time evolution.
I'm not sure. Okay, I'm not sure if I can answer that because I don't know what you mean, but I can give you a different answer that might answer your question. So when you only have one of them, the spectrum is off by a lot from Haar. And one of the results from random matrix theory says that this GUE ensemble, Gaussian ensemble, has a semicircle distribution, whereas a random Haar, like a completely random unitary, should have a spectrum that's like uniform around the unit circle. But the bases are distributed the same between this GUE and Haar random matrix. So I don't know if that somehow
That helps.
correlates to the energy conservation, but that's where the key difference is. Yeah. I don't know, Patrick, do you have a?
I think that's a good answer.
Okay. Okay, so now I'm gonna move on to computational pseudorandomness, and also our linear T design. Does anyone, this will be kind of a new topic. Does anyone have any questions about the previous?
Sorry, just to follow up on Aaron's question. But yeah, during this, for example, if you do E to the IC that G, in which G it has a symmetrical distribution, how do you know E to the IC that G is not unit?
So
Like for
GUE has factors, the basis and the spectrum. So it has like an eigenvalue decomposition. Specifically, the basis will be Haar random, and the spectrum will be diagonal. Then you just, you know from linear algebra, you can just, when you exponentiate that object, you just exponentiate the diagonal. So yeah, you're right. It won't be semicircle, but it'll be e to the I semicircle, which still is like, there's no whiteboard, but it's still like weight. Yeah, I don't know if people can see in the table marker, but it'll be like weighted kind of like on, this is a semicircle. All of the weight will be on like the side of the semicircle, as opposed to being like uniformly around the semicircle. We can talk offline about it as well. Yeah. Okay, so this work on computational pseudorandomness and also linear T designs is a follow-up on our previous paper. And I just wanted to mention this was jointly released with Metger, Sinha, and Yuan, I forget the P. And both of these works jointly achieved computational pseudorandom unitaries and also linear T designs. That seems a little bit strange, but there's a reason for this. And we'll see later that both of these works are heavily based on a specific primitive, which is a pseudorandom permutation, or random permutations, essentially. So permutations are a common theme. And this follow-up work, it has a different construction, so it's based off of permutations, but a lot of the proof techniques are very, very similar.
Sorry, just on the previous part, why was it all T squared?
Why was it only T squared?
So, could you explain where the all T squared comes from?
Oh, yes. So, I would say intuitively, this comes from the limitations of of convergence of due to the central limit theorem. If you remember from your probability classes, the convergence of IID random scalar random variables that match the low moments of a Gaussian random variable, that converges in squared time. And it kind of comes from the square root, but the scaling comes from is analogous to the scalar case. I don't know if that provides any.
Is M order T squared?
Yes.
Okay.
Yes. Yeah. That's that's basically it. Okay, so Michelle defined T designs, but now I'll get into the definition of computational pseudorandomness. And first, I'd like to draw an analogy to classical cryptography because this is a cryptographic definition. And if you might be familiar, or you might not be familiar, I think it's still a good analogy. So what is a pseudorandom function? A pseudorandom function is a family of functions on n bits, like classical, and with a secret key. And these functions without the secret key are indistinguishable from a truly random function, truly random function on n bits. And by indistinguishable, I mean that there's some adversary sitting on the internet, hacking your computer or whatever, reading your messages, and it has access to polynomial resources, but nothing unreasonable. It doesn't have infinite time. And that's what I mean by polynomial time adversary. And I'll use this double again to represent a polynomial time adversary. And these functions are used, or like we use them every single day. They're important for things such as like message authentication codes and symmetric key encryption. These are just like very, very useful things that we use on our phones every single day, although you probably don't use it specifically or knowingly. And by analogy, we can define a pseudorandom unitary. So formally, if this U is a Haar random unitary, or just a uniformly random unitary, we say that a random unitary V is pseudorandom if first it has an efficient circuit. So by efficient, I mean polynomial size circuit. And also again, polynomial time adversary cannot distinguish U from V with high probability. And so pictorially, this is what it looks like. We say that we have, so I only have 4 rows, but you can think of there being polynomially many rows. And we have this adversary, which can do arbitrary polynomial time computation before to prepare a state. And then it can access this random unitary or Haar random unitary, it doesn't know which, polynomially many times. And then it can do some post-processing, but again, it's bounded by polynomial time. And then it can do some measurements. And we say that this random unitary V is pseudorandom if this output measurement is like very close to that of a truly Haar random unitary.
When you say polynomial time, you mean polynomial time in the number of qubits or polynomial time in the dimension of the Hilbert space?
In the number of qubits, because if you had polynomial time in the dimension, you could just construct a Haar random unitary. Yeah. But that is an important distinction. Oh, and also, it's not written anywhere on the slides, but little n we use as the number of qubits, and big N we're using as the dimension size. Okay, so again, as before, I'm going to throw a big blob on the screen and then break it down. So this is our construction. It looks different, but let's break this down. So these AMs are normalized sums of signed permutations. So the first thing is we take ZA and we add its complex conjugate so that this is a valid Hermitian Hamiltonian that we can simulate. And this ZA is distributed as a diagonal matrix times a permutation matrix. So here's the beginning of the permutations that I mentioned earlier. This diagonal matrix is just a random diagonal matrix with random phases. And this P sub A is a random permutation matrix. So it's just permuting all of the elements, and it's a sparse matrix. Again, theta is an order 1 constant. You don't have to worry about it. And then we're taking a bunch of products of these. So before we only had 2, and now somehow we're getting bored by taking more products. And then finally, these Z's are also distributed the same as these Z's up here, meaning it's just a diagonal matrix, random phase, and a permutations. And this is where a lot of, our analysis this is where like what our analysis relies on. Here I wrote allows use of the partition algebra. What this means is that because we're multiplying before, or we're applying a random permutation before and a random permutation after, this somehow restricts V to V now has some symmetry, and namely it's invariant to random permutations. And this invariance is what allows us to effectively restrict the potential like set of measurements that you could perform. And this what allows us to then analyze this object and show that it's close or indistinguishable in some way to Haar. These are details. You don't have to worry too much about it. But this object, our theorem is that this object is a PRU, a computational pseudorandom unitary, when you replace those permutations with pseudorandom permutations. So the ones in these Z's and also in these A's, if all of those were replaced with pseudorandom permutations, then this object is a pseudorandom unitary. Mark Zandri showed quantum secure pseudorandom permutations exist in 2016. And then it also turns out that this object is also a linear T design if you replace those permutations with T-wise independent permutations. So again, by T-wise, so the previous one was theorem 2 is a computational pseudorandomness, and then theorem 3 is like back to statistical pseudorandomness. And by T-wise independent permutation, what we mean again is the statistical notion of closeness, in that this permutations match T moments of a truly random permutation. And I also wanted to mention that this result on the linear growth achieves linear circuit complexity growth as well. So basically, T designs, this ensemble of circuits also achieves that linear like circuit complexity growth as well, which in comparison to roots T circuit complexity or roots to the 10. So, and again, this is optimal.
Sorry.
You would you like to? Okay, we can end in.
You have time, you can end, yeah, the room is yours, but it's 12:40.
Well, do people want to hear about some proof techniques, or this is what? Okay, we can end here, and then if people people are interested, we can go into it. So
If you want to hear about proof techniques, you can ask about them.
We have a lot of extra slides, like a lot.
Okay, so in conclusion, pseudorandomness plays an important role in substituting for true randomness, and it has both computational and physical applications. And what we showed is that we've achieved T designs with linear circuit depth, and this is optimal by a counting argument. And we also achieved computational pseudorandom unitaries jointly with another group as well. And something that Michelle and I we're all excited about is more a few very interesting random matrix theory techniques, which we did not discuss. And yes, that's it. Yeah.
So the PRU construction is parallel query secure, or it's like, what is the
Yeah.
you conjecture that it's actually just a PRU, but you don't know how to prove what?
Okay, yeah, so so Sean is asking about the details of our definition of a computational pseudorandom unitary, and specifically, this is for a parallel PRU. It could be an adaptive PRU, but we didn't have the tools to analyze it properly.
So the picture of the like
Yeah,
circuit
you notice
picture-
that this is.
yeah, okay, so there's no adaptivity in this.
Yeah.
one. Okay, got it.
The picture is accurate. For the
Yeah, got it. Thanks.
Yeah.
On your definition for the linear scaling, you had this parameter L that determines how many terms are in the product.
The definition, oh, here.
Yeah, in the construction. And so I guess I'm wondering, how do you choose this L? And what does it buy you as you go to more and more terms? Is it something like the randomness or the scaling changes?
L should be polynomial, I believe. So something that's not too much time. I would imagine that all of these constructions, if you just take, okay, definitely if you take like a bunch of products like some exponential or exponential, then you'll get something that's close to, I mean, you'll get something that's truly Haar random. But the trickiness, I mean, that's true of the other construction as well. But the trickiness is how to get something that's efficient to construct or to implement on a computer that somehow spoofs this randomness appropriately. Yeah. Yes.
So what does the spectrum look like for this, the ensemble that you're putting in the exponent, like the AMs, what does spectrum look like?
Okay. Yeah, so actually this is where the analysis is similar to your previous result. Again, when you take these, okay, actually it wasn't completely necessary. We would analyze things in a different way, but I would, whenever you take, this is like a basic random matrix theory result. If you take random matrices that match like very small moments of a Gaussian random matrix, it's like kind of a universality statement. And you take, if they're IID and they don't have like terrible statistics, like it's,
So
you don't have infinite second moments, then if you add them up, then they get close to Gaussian. And
right, so this is just the central limit theorem, but you're saying that you have the equivalent thing to the central limit theorem for matrices. So I guess in the first construction, you're just like, I have some bad technique of generating a GUE. I sum a bunch of them, it's a better GUE.
Mhm.
But now you told me I have this specific way of generating sort of a bad GUE. And then you're not taking a sum in the exponent, now you're taking this product over like them exponentially.
okay, so we have a sum in addition to a product.
Oh, okay.
Yeah.
But this is the same idea that like this is supposed to be like a sort of mediocre work method of generating a GUE.
I think that there might be one, so you're right, that probably is true, and that might be one way of analyzing it. But we actually needed to move to a different or use a different technique to analyze this object due to the, I think probably the same limitations I mentioned before. Okay, so intuitively we're taking like sums and more products to hopefully like balance it out and mix things more. But what the analysis really required was taking these exponentiated permutations and expanding out the exponential into a Taylor series. And now we have a product of a sum of like a Taylor series of a bunch of permutations. And somehow we're able to show that in the large n limit, when you like multiply two permutations together, even if they're correlated, they are approximately 3, and they when you take products, they actually don't look that correlated. And that you take, even if you take the same permutation and you apply it 2 or 3 or 4 times, and you look at the input output behavior, it looks like a random permutation. And somehow this ingredient is one of the key ingredients that got us the better linear scaling. I don't know if
That's because like if I have a permutation in the large n limit, like its orbit is infinite, so like it never looks, it always just creates a different permutation.
Yeah, that's exactly it. And then, you know, unfortunately the n dimension is large, but it's not infinite. So that's where we used our previous technique of this getting finite n corrections of large n limit to like interpolate back to finite but still large n. But the intuition is correct.
Thank you.
I will also say The other construction, we didn't get into this, we just told you there is some HJ that's gonna match the Gaussian movement. But we do have a very realistic construction for that as well, that doesn't use permutations, but it has like a different. So it's not just like, oh, you also need to assume that there's, some Gaussian design that you're making. It's like, we actually also have they're both very concrete, just in different.
I think you could go ahead.
I guess this was like all motive, or a lot of it was motivated in terms of like scrambling. Dynamic
Well-
kind of thing. So I was wondering, like, if you have like some Hamiltonian that is a scrambler, say, like, to what extent does that, like, some family of Hamiltonian scrambling, to what extent does that fall into the same like Haar random? Yeah, or is it like,
No, Michelle, do you have an answer to this?
Oh, it depends on exactly what you're looking at. That's definitely a way that you can see. The harder thing is moving, like intuitively, you would say there should exist Hamiltonians that create amounts of, randomness. Things that they do is scramble, but the other thing that they would do is start to match moments. But then you need to prove, well, first of all, you need the techniques to prove what moments it's matching and how well it's doing that really. And even in the case of random unitary circuits, the technology is constantly improving in just like the analysis. But then in the pseudorandom case, it's even harder because we have fewer of those two. So like intuitively, that's the right direction, but it's just.
I think there's an important distinction to be made as well, which is just that if you have a single fixed Hamiltonian, you can't satisfy either of these definitions because you have one unitary, and you can determine that's not Haar because it's a specific thing that you can check against. So you need somehow an ensemble of scramblers. And there is a paper by Brian Swingle and others that shows and uses path integral techniques, so it's not rigorous in the sense, but it's pretty convincing that a continuous time random walk on the unitary group generated by sort of k-local interactions will be a T design in linear time, but then you also have to simulate that thing and prove that it converges. That has to be done.
Yeah, I didn't see the order, sorry guys.
So before you explain that you have the GUE with like a sine circle and you exponentiate it, so it becomes like a flower with one petal, something like that.
Yeah.
And then so if you have two, is the intuition that you have, or you have more, like does that mean like you have like the petals would cover the circle, or is not is that like
You're asking what the spectrum looks like when you have two.
So why would having like more would help to make it better, and also, yeah.
Yeah, somehow like the spectrum of your original, you have two objects and the spectrum of each of them don't matter too much. Actually, what matters, or the thing that buys us this closeness to Haar, is the basis of each of these. So the exponentiated Gaussians each have a Haar random basis. And one of our key lemmas was saying that if you have two objects and they both have independent Haar random bases, then the only thing that you need to look at are the trace moments of this one object. And if the trace moments of this one object is small enough, then that's actually something that's close to Haar. So it's called like small moments implies Haar. And we're able to show that when you take the product of these two exponentiated Gaussians, I don't think I could describe to you what the spectrum looks like in terms of like petals or something that has like a nice form or a nice polynomial, but we were able to show that the trace moments of that combined object they're just small. And that due to some marginal limit polynomial interpolation, due to like Weingarten calculations. And because it's, yeah, I don't really know what it look like. It's very close to Haar, so it would look probably like uniform with like weird bumps around it. That's probably not a very satisfactory answer, but you could have started with Haar and a basis and like different spectrum. So we didn't actually care that it was specifically semicircle to start with, as long as it's something that's like, when you multiply them together, we get small trace moments, then that's good enough. So it just so happens that because of universality things, everything, when you sum them up, converges to the semicircle distribution. So that's what we were working with, but it's actually not that important to our.
So does it matter actually as a finite? So say the symmetrical circle is would be like the support would be finite, and then when you exponentiate, so you can see that the original support is finite, so you can't like cover the whole circle like in one shot. But then does that matter? So if say you have just some finite support and you exponentiate that, and then you multiply several pieces together, is that intuition that that kind of thing would be smeared out, so it's no longer like the finite support wouldn't like.
I think actually the problem is not that the support is finite, because for example, if your G had Haar and a basis, and then it was like uniform from negative pi to pi. From negative pi to pi, like there's like a uniform distribution on it. Then if you exponentiated that, well, okay, ignoring like eigenvalue repulsion and things like that, if you exponentiated that, you would get something that's uniform around the unit circle, right? So it's not the fact that it is finite support, but that it's not uniform looking.
Sorry, I was more like saying that it would taper off at the end point, so it would go to 0 at the end.
Oh, yeah.
So like is it related that if you put like more copy of it, it will cover the circle better?
I think that's the right iteration, because the importance is these two matrices have different eigenvectors, but it's not just about eigenvalues.
Yeah.
Oh, okay.
Yeah.
I don't, so I think like one picture maybe that you're trying to get at is like, oh, like, you know, if you exponentiate one Gaussian for a little bit of time, you end up with like a bump somewhere. But what if you like added more of them so that there are like bumps around the entire thing, and then that like the picture?
So you think it's not like
It's not like that.
Oh,
Because
okay.
there's some complex interaction of.
Yeah, because
G1 and G2 don't commute.
Oh,
So you
okay.
can't use it.
but you are right that like, it is true that if you start with a semicircle, and if you like are able to smear this out by taking this theta to infinity, like you can get something that looks like smeared out like this. And this would wrap around the unit circle. Yeah. Okay.
It's like the marker, you doing the marker.
No, it's okay. But if you take theta to infinity. Oh, actually there's a slide. Oh no, it's not there. Oh, here. So we have like this circle that's uniform this, and if you took theta and you took that to infinity, this would like start wrapping around the circle and getting smoother and smoother and smoother. And actually, when you take that to infinity, I believe that's a Haar random matrix, but it will grow. You need theta to be like exponential for you to get an exponential. Yes.
Yeah, in your construction, is there an easy way to see what the circuit would look like? Can you drive that easily, or in general, like what does the circuit implementation of that look like?
Yeah, we do have a circuit construction. I don't think I have a good image of it up here, but it really is based off of this object right here. And if you look at this sum, there's a way to take a bunch of Hamiltonians and block encode or construct a sum of these Hamiltonians with, and then if you have this object, which is the sum, we're able to, their Hamiltonian simulation technique to then Hamiltonian simulate it for like a theta over root m time, or just theta time. So that's basically what we just use those techniques, mainly QSVT, and LCU is the linear combination of unitaries. And then we just do that twice.
Okay, so it looks like Hamiltonian simulation. Or
Yeah, these H's are Hermitian matrices, so it does look like Hamiltonian simulation. Like a bit fancier than Schroederization, but they're still off-the-shelf methods.
And that would be like linear or t squared.
For this one specifically, the depth would be t squared, but yeah, that's what I'm talking about, is the circuit depth of this.
So you mentioned ADS CFT. Oh, what was it, Sam? Not me. Yeah, why don't we?
Yeah, he's been waiting for a while.
Okay, yeah, so if you go to your newer construction, the linear in T, and you actually like wrote it as a circuit, is there some intuition of what that circuit would look like?
Again, this would be similar to what I just said, but instead, we have this linear combination of permutations, and those permutations, if they're the pseudorandom ones, then we use the circuit from those quantum pseudorandom permutations, which would have a secret key. And then if they were if it was a T design, linear T design, then we would use that like linear depth permutation design. There's actually a paper coming out soon constructing key ingredients for those permutations. So yeah, but other than that, it's the same. You take a sum of them, you Hamiltonian simulate it, and then you do that L times for independent permutations. Yeah.
So in this sum, is it is there also shuffling of the eigenvectors?
Yes, the diagonals are, is that what you mean? Oh, wait.
I mean, in the sum, among different summands. Eigenvectors are totally,
These? Wait,
yeah, among Z1 and Z2.
yeah, each,
They can be,
no, because permutations don't commute.
The D's are all diagonal on the same basis, but they're multiplying these permutations.
Yeah, okay. Yeah, back there.
So you talked about connections with ADS CFT. Is the connection just like if I want to do simulations with a linear ramp, I need some technique like this, or is there? Did this actually involve like a holography calculation at some point?
Yeah, Michelle can answer this one.
There are no holography calculations in the two papers that we have. I also, the connection is not so straightforward as like, oh, if you wanted to simulate ADS CFT, you would use one of these. I don't, it's not, it's like, there's a few more steps before that. It's like, well, you want to model ADS CFT and the dynamics of the sort of growth of the wormhole volume, then you would want something that sort of the complexity grows as linearly, and this is something that does that, but that's not a claim to say that these are the same.
Okay.
I'll show it to you.
I lost it.
Yeah, go ahead.
Yeah, I was wondering whether you have ideas of either like tasks or near-term experiments in quantum simulators that could be interpreted as implementing something like these constructions. And I guess I'm inspired a little bit by thinking about significant work by Michael Endren and Sun-Won Choi on pseudorandom and the interacting spin chain of Rydberg atoms. I think that's a little bit like just having a single fixed Hamiltonian. But is there something where, you know, you vary the parameters and then it starts to look like your first construction with H and H prime, that type of a system?
Where you vary the parameters of.
Vary the parameters of the Hamiltonian. So experimentally, you have some knobs that you could, you know, change some parameters in the Hamiltonian that the spin chain is evolving under. So then maybe you can implement like evolution under the HJs followed by the H primes or.
Oh,
yeah.
So like more of a, would that be more of a like Trotter type of?
Doesn't have to be a Trotter. Yeah, now maybe I'm forgetting what exactly the construction was. Do I need to alternate between?
I
Sequentially do one and then the other. It's just really just It's basically just sequentially evolving under a Hamiltonian that's the sum of the H times and then a Hamiltonian.
Do you have,
Right. Maybe,
Yeah, I think maybe I have a response to that.
yeah,
You get a lot of mileage by taking ensembles that are not T designs themselves, like they're not the mixers.
Uh-huh.
And then you then just take a product of many of them, 2 of them, 3 of them, L of them. And
right,
that kind of makes up for the deficiencies of the scrambling.
right. I mean, here it's just 2 of them.
You're
right?
just 2,
It's
yeah.
just
and
like,
then the other
it
ones-
looks like I evolve under some Hamiltonian and then I evolve under a different.
Exactly, of course, in this one, we
And-
have to take n big, like we have to take a sum of a bunch of things, and the other one, you can put n much smaller and make up for it by running L, right? So somehow like, we're making up for a small number of sum n's by just taking a product of many of them, and that fixes it. So there is, yeah, I do see some like high level inspiration there that we get better.
What's the
scrambling than-
scale of the M again, if I have like n cubits, M? How big?
oh, M scales with T,
Yeah, okay.
so it would be T squared roughly. Yeah. So depending on what design you're.
Right.
Yeah.
Yeah, okay.
Yeah, we haven't thought about it very much, but I think it's worth, like, these constructions, I don't think are too hard to implement.
Do,
But
sorry,
the
yeah.
techniques,
Yeah.
and the general principles, as Adam was saying, I think could lead to, like, with thought, like things that might be more practical to run.
Do here, do the H phase, like, do they need to be local? Can they be local? The H phase, can they just be like products of
So,
Howley's neighboring sites? Right, or,
so
yeah,
No, not this case, but just.
I think they could be local if they also, and you would probably get worse scaling. Because in the end, if you take sums of them, then you'll get something that looks close to Gaussian by those same results. You'll get the, but you won't get the probably optimal scaling that we have. You might not care about that.
I think with random policy that like something like that instead
Yeah.
of T squared.
Uh-huh.
It would still get there.
It still would have been the state of art a year ago.
So random polys are pretty.
so it kind of seems like if you had like some Hamiltonian that was used as strongly interacting spin chain and then a different one. Essentially, it's like pretty good, probably, and better than just one.
Yeah.
That's probably true.
Yeah.
Yeah, I think that's interesting. It
And when-
really requires, we weren't like viewing it from that lens as much, but it's probably worth analyzing. Like if you take something a bit more physical, what can you get?
Thanks.
All right, I think it's a good thing that you, was there one last question?
I was just gonna ask, like, if you use like measurement for local measurement, for example, instead of evolution, if there's any like wind there.
By measurement, you mean like measurement-based computation? or-
Just like I can like measure a qubit and change what I do, and that's sort of like a give me some capability that I don't have just with unitary evolution.
The adaptivity.
You're talking about like the accuracy. Or-
No, for the like simulating.
Oh, for simulating.
Yeah.
Well, I think there's a result that measurement-based computation is like equivalent, or the things that you can do with measurements. You can push all the measurements to the end and that should be the same. So I don't think it would buy you anything. Oh, yeah, we also haven't thought about that specifically. And also, if I misunderstood your question.
I was gonna say, I think it's a good thing that you left off time for questions, so if there were a lot of questions, so let's thank Michelle and George for their.
Sounds like-